Hey Eleanor, I'm a little sick, so I'm trying to stay focused and get this for you. But I'll just show you how I solved this because my process might be a little different than yours. I always start out with the IR and then I move to the HNMR. But as I go down through it, I just kind of look for anything that stands out as unusual. So starting with the IR, I go overtones of a ring. And then I say CH2 double or CH double bonds, sp2 carbon. And then you're right on this carbonyl. That's great. It is not going to be a carboxylic acid, we know. So it's either going to be a ketone or an aldehyde. Okay. And then I go through, the only thing you're looking at the MS spectrum for is really the presence of a halogen. So, and if there's a formula. So there's nothing interesting on there, so I'm not going to look at that yet. I'll just use it to corroborate. And then I kind of overlook CNMR, and I just kind of, what I like to do is make sure that there are signals pointing in, both up and down. And it looks like there aren't any pointing down. So there's no CH2 carbons. So that's going to say something about how we draw our picture. We can't have anything that looks like that. We would have to have something like that for it to comply to the CNMR. So no CH2 carbons. And so that's worth noting. Now we go down to HNMR. So these have these kinds of lines. I forget what they're called. But it means that these two are going to have the same number of hydrogen. Okay? This one, the aromatic, is going to have the most, which means it's probably 5. It's going to be 4 or 5. But then the shape of this also says something about if it's 4 or 5. So this is kind of right on the edge, but for the spectra for things that are p substituted will show up in like 2 very clear doublets, because like this has a signal and this has a signal. That's not the case here, so we know it's only mono substituted. So it's going to look, so this is what we're learning at each stage. We know that we have something that looks like this, and we know that it can't look like this. It would have to be like that. And so now we look at how many carbons there are. There are 9 carbons. So we have 6 here in the aromatic ring, 6, 7, 8, 9. Okay, so that takes care of our carbons. Now let's add an aldehyde here, because we know that's going to be an aldehyde in part because of where this signal is. That's your aldehyde signal. If it was a ketone, the signal's over in like the 12 area, I think. It's farther over. So we're just going to stick that aldehyde there, and then we're just going to confirm that everything looks good. And I'm going to let you do that yourself, so this isn't too long.